Hello, today we will be analyzing conventional sand casting compared to 3D printed mold casting, a presentation by Rahul and Anantakrishnan. Our objective today is to provide a technical and economic comparison of these two manufacturing methods. We will evaluate the capabilities of the advanced process against our current baseline to determine the best path forward for the company's new manufacturing line investment. To begin, it is important to define the specific advanced manufacturing process we are evaluating. While the application is broadly called 3D sand printing, the specific industrial process is known as binder jetting. Unlike metal 3D printing that uses high heat lasers, binder jetting is an ambient temperature process. It takes a digital CAD file and slices it into layers. The machine spreads a thin layer of standard foundry sand and a printhead moves across it, selectively depositing a liquid binding agent, essentially a glue. It repeats this layer by layer, and the result is a sand mold that fits directly into our existing casting workflow, but it was created entirely digitally. So, how do these processes differ for our operations? Conventional sand casting is fundamentally a physical forming process. We rely on a hard pattern, place it in a flask, and use mechanical compaction to shape the sand around it. The physics of this process are defined by the need to physically pull out that pattern out of the sand without damaging the mold walls. Binder jetting removes that physical constraint because it is an additive process. There is no pattern to insert or remove. The printer reads the CAD data and chemically bonds the sand only where the design requires it. The fundamental comparison here is shifting from a physical forming with all its geometric limits to digital construction where those limits are removed. This shift to patternless manufacturing leads our first major advantage: geometric freedom. In traditional casting, we are constrained by positive draft angles and parting lines. We must ensure the pattern does not degrade the mold during removal. We also struggle with undercuts without complex core assemblies. With binder jetting, since there is no pattern withdrawal, we can print zero draft features, deep undercuts, and complex internal channels. This allows our engineers to transition from design for manufacturing to design for performance. The second major advantage is the impact on our supply chain. Currently, the lead time for a new casting is measured in weeks or months because we have to wait for the tooling shop to machine the pattern. With the printer, we can go from a CAD file to a poured casting in just 2 to 3 days. This also enables what we call digital inventory. Instead of paying to warehouse thousands of legacy patterns that we might only use once a decade, we can store them as files on a hard drive and print them on demand. However, we must balance these advantages against the limitations of the process.
Now let's look at some of the production limitations. Despite the benefits, binder jetting faces serious production constraints. The technology prints molds layer by layer, which is significantly slower than simply packing sand around a pattern. For our company, that means low throughput and limited scalability. Printer build volumes also limit the maximum size of parts we could produce. And after printing, molds must be depowdered and cured. This adds time and labor. These limitations make binder jetting unsuitable for medium to high volume parts in our production environment. So now let's look at some of the quality limitations. Printed sand molds tend to produce rougher surfaces compared to molds made from precision machined patterns. Thin features may be fragile, especially during depowdering. If the binder doesn't fully saturate or if the binder saturation is off, we could see dimensional variation or weak mold sections. And depending on the metal we are pouring in, the binder breakdown can introduce gas or inclusions. None of these issues are deal breakers, but they do require tighter process control than our current setup. Now, let's talk money. From a cost standpoint, the comparison is pretty straightforward. Traditional costing has a big upfront cost, that's tooling. But once we've paid for it, each additional part is extremely cheap. That's why it works so well for our high volume products. Binder jetting removes the tooling cost completely, which is great, but the mold itself costs more. Binder, machine time, curing, and depowdering all adds up. Because of that, binder jetting usually becomes cost effective only when we don't want to pay for the tooling and when the geometry is way too complex. So again, it's great for specific cases, but it won't beat conventional casting for the day-to-day parts that we manufacture in large volumes. So let's look at the reality. When we looked at vendor materials, most of it highlighted the positives, such as the speed, complexity, and how tooling is eliminated. What vendors don't talk about much are the real constraints: rougher surfaces, slower throughput, and higher variable cost. Academic research gives a more balanced view and confirms those limitations. When we evaluate everything, binder jetting lands around MRL 7 or 8. That means it's proven in pilot productions and certain industry applications, but not mature enough for full scale, high volume manufacturing environment like ours. So, what does all of this mean for our company? Based on the process, cost, production, and readiness analysis, binder jetting absolutely has a place, but a very specific one. It makes the most sense for prototyping, low volume or custom parts, complex geometries that are hard to tool, or legacy parts where patterns don't exist anymore. For our high volume casting, the everyday production that keeps our facilities running, conventional sand casting is still the better option. It's faster, it's cheaper, and more predictable. So, our final recommendation is this: binder jetting should complement our existing casting processes, not replace them. It gives us the agility and the design freedom where we need it, but the traditional casting still remains the backbone of our high volume productions.